So let us define tensors. A tensor is a set of quantities called components whose properties are independent of the coordinate system used to describe them. For two different coordinate systems, the components of a tensor obey specific transformation laws. So we shall see certain examples to understand this definition later. So let us introduce some standard notation and conventions that is being used or being followed in tensor analysis. Let us consider an n-dimensional space denoted by V subscript capital N, and let x superscript 1, x superscript 2 up to x superscript capital N be any set of coordinates in the n-dimensional space V subscript N. A point to note here is that x superscript 1 and x superscript 2, where the superscript do not indicate the power of the coordinate. So these superscripts are merely labeling the coordinate in the n-dimensional space considered. They are merely a superscript. Suppose if we want to use superscript and power together, we may express it by denoting x superscript I within bracket and the power outside the bracket as shown here. Now let us consider another set of coordinates denoted by x bar superscript alpha, where alpha takes the values from 1 to n in the same n-dimensional space Vn. So here a point to remember is that there are two sets of coordinates indicated here. One is a barred coordinate x bar and the other one is an unbarred coordinate. Conventionally, for barred coordinates, the superscripts are denoted by Greek letters, whereas for unbarred coordinates, the superscripts are denoted by Latin letters. So clearly, each of these coordinates x superscript I will be a function of x bar superscript alpha and vice versa as shown here. That is, x superscript I can be expressed in terms of x bar coordinates and x bar superscript alpha can be expressed in terms of x superscript I coordinates, namely x superscript 1, x superscript 2 and so on and so forth. So in this equation, the I value have the value from 1 to capital N in the n-dimensional space, and in this equation the alpha value has the value from 1 to capital N in the n-dimensional space V subscript N. So we can understand the previous discussion with the following example. So we have a unbarred coordinate system and a barred coordinate system. For an unbarred coordinate system, let us consider a Cartesian coordinate x, y and z in a three-dimensional space. And for a barred coordinate system, let us consider r, theta and phi, that is the spherical polar coordinate in the same three-dimensional space. So in the Cartesian coordinates, x, y and z are independent of each other. So similarly, in spherical polar coordinates, r, theta and phi are independent of each other. However, the coordinates of one set can be expressed as functions of another set. So the Cartesian coordinate x can be expressed in terms of the spherical polar coordinates as given by this expression, x is equal to r sine theta and cos phi. So similarly, y can be expressed as r sine theta sine phi and z can be expressed as r cos theta. So the inverse transformation, that is, we can express the spherical polar coordinates in terms of Cartesian coordinates as shown here. That is, r is equal to square root of x square plus y square plus z square and theta is equal to tan inverse square root of x square plus y square divided by z, and phi is equal to tan inverse y by x. So now let us consider an unbarred coordinate system and a barred coordinate system as discussed before, and we take the same example of a Cartesian coordinate and spherical polar coordinates. So here we have x is equal to r sine theta cos phi. So x can be expressed as a function of r, theta and phi. Suppose if we differentiate x, so we have dx on this side. Since x is a function of three variables, we have the partial derivative summation as indicated here, dou x by dou r dr plus dou x by dou theta d theta plus dou x by dou phi d phi. So similar is the case for the barred coordinate system. So here the spherical polar coordinates are expressed in terms of Cartesian coordinates x, y and z. For example, r is equal to square root of x square plus y square plus z square. Or we can say r is a function of x, y, z, and hence if you differentiate r, we have dr is equal to dou r by dou x dx plus dou r by dou y dy plus dou r by dou z dz. So if we generalize this differentiation for this unbarred coordinate system as expressed in this equation, we have dx superscript I is equal to sum running over alpha is equal to 1 to capital N dou x superscript I divided by dou x bar superscript alpha into dx bar alpha, where I takes the value from 1 to N. So similarly, we can differentiate x bar alpha as dx bar alpha is equal to summation I is equal to 1 to n dou x bar alpha divided by dou xi dx superscript I. Again, the value of I runs from 1 to n. So there is a convention used to simplify the notation for the right hand side of these equations, called as Einstein's summation convention. So according to this convention, if an index except capital N is repeated in a term, summation over it from 1 to n is implied. For example, here the summation runs from alpha is equal to 1 to capital N, and the index alpha is repeated in these terms dou x bar alpha dx bar alpha, and hence we can drop this summation sign and express this equation in this simple manner as dx superscript I is equal to dou x superscript I divided by dou x bar alpha dx bar alpha. So likewise here the summation is running from I is equal to 1 to n. The index I is repeated in this term twice, and hence we can drop this summation. So according to Einstein's summation convention, this can be expressed as dx bar superscript alpha is equal to dou x bar alpha divided by dou x superscript I dx superscript I. Now let us define free index and dummy index. Suppose if an index appears only once in any term, it has a definite value between 1 and n, and such indices are called as free index. For example, in this equation and in this equation, I and alpha appears once and they are free indices. For example, in this equation as well as in this equation, again I and alpha are the free indices. So dummy index is an index which is repeated and over which summation is implied is called as dummy index. For example, here we have I as a superscript which occurs in two terms and hence the summation is implied here. So the summation is implied to this index I, and this can be suitably replaced by any other symbol, let us say k. So dou x bar alpha by dou x superscript k dx superscript k is exactly equivalent as to this expression. So let us consider some other examples to understand free index and dummy index. So now let us consider this expression. Summation I is equal to 1 to capital N a subscript I and x superscript I, which is equal to a subscript 1 x superscript 1 plus a subscript 2 x superscript 2 plus and so on a subscript n x superscript n. Here the index I is repeated more than once in a term, and hence according to Einstein's summation convention we can conveniently drop this summation symbol. Moreover, since this index is repeated and over which the summation is implied, hence it is called as a dummy index. So this summation can be expressed in Einstein summation convention as a subscript I x superscript I. Since I being a dummy index over which the summation is implied, we can equivalently express it as a subscript k x superscript k, or with some other labels as a subscript j x superscript j. Now let us consider four sets AI, BI, CI and DI of n quantities where I runs from 1 to n. Then according to Einstein's summation convention, a subscript I, b subscript I is exactly equal to a subscript 1, b subscript 1 plus a subscript 2, b subscript 2 plus and so on plus a subscript n, b subscript n. So here I is repeated in a given term and over which the summation is implied. Hence this is a dummy index. Hence AI, BI can be expressed with other labels as well, as shown here AJ, BJ or AK, BK, etc. Now consider AI BJ, CJ is equal to AI B1 C1 plus AI B2 C2 plus and so on AI Bn Cn. So here I is the free index because it appears only once in a term, whereas j is appearing twice over which summation is implied, hence it is a dummy index. Hence this expression can be suitably expressed in this fashion as well, that is AI Bj Cj can be expressed as AI Bk Ck or AI Bl Cl. However, a point to remember is that this dummy index cannot be replaced with a free index. That is AI Bj Cj is not equal to AI Bi Ci. For example, if you consider this part AI Bi Ci, then we have on this side A1 B1 C1 plus A2 B2 C2 plus and so on An Bn Cn, which is not equal to this expression AI B1 C1 plus AI B2 C2 and so on and so forth. So now let us define what is Kronecker delta. So in the previous slides we have considered two different coordinates. One is a barred coordinate and the other one is a non-barred coordinate. For an unbarred coordinate, we have considered the example of Cartesian coordinates x, y, z, and for barred coordinate, we have considered the example of spherical polar coordinates r, theta, and phi. So, in a Cartesian coordinates, x, y, z, they are independent of each other. Likewise, r, theta and phi are also independent of each other. So if you generalize to this notation, the coordinates x superscript I are independent of each other. So the derivative dx superscript I by dx superscript j will take the value of 1 only if I is equal to j, otherwise it will take the value of 0. So this is expressed by a symbol called Kronecker delta, indicated here as delta superscript I subscript j. So this is called as Kronecker delta. When I and j are equal, Kronecker delta will take the value of 1, and if they are not equal, the Kronecker delta will take the value of 0. So this is same if we consider the barred coordinates x bar alpha. So the dx bar alpha divided by dx bar beta will take the value of 1 if alpha is equal to b, otherwise it will take the value of 0. So in this case we can denote the Kronecker delta with the index alpha and beta as shown here. So delta superscript alpha subscript beta is the Kronecker delta corresponding to this derivative. Since the coordinates xi can be expressed as function of x bar superscript alpha, we can write or rewrite dx superscript I by dx superscript j as a partial derivative as shown here, that is dou xi by dou x bar alpha to dou x bar alpha divided by dou xj. So this is nothing but the Kronecker delta. So either we can write dx superscript I by dx superscript j as delta ij, or this partial derivative dou x superscript I by dou x bar alpha by dou xj is equal to delta ij. So similarly we can write for the barred coordinate system dx bar alpha by dx bar beta as delta alpha beta with this partial derivative. The Kronecker delta, as shown here, delta ij takes the value of 1 if I is equal to j, otherwise it is 0. So some of the examples are shown here. Delta subscript 1 superscript 1 is equal to 1, delta 2 is 1, delta 3 is 0, and so on and so forth. So delta superscript I subscript k into x superscript k is equal to x superscript I, because all the other terms will vanish, and hence sometime delta I k is called substitution factor. Now let us see some other definitions. Conventionally, the superscripts are used to denote the components of a contravariant tensor, and the subscripts are used to denote the components of a covariant tensor. So we shall shortly discuss about the contravariant tensor and covariant tensor. The components of a mixed tensor is denoted by both superscripts and subscripts. For example, x superscript I are components of a contravariant tensor, b subscript ij are components of a covariant tensor, c superscript I subscript jk are components of a mixed tensor. Now let us define what is the rank of a tensor. Rank of a tensor is the number of indices appearing in the symbol representing the components of a tensor. For example, here x superscript I is having a rank of 1. So this is a tensor of rank 1. Here we have two indices I and j, hence bij is a tensor of rank 2. C superscript I subscript jk, we have three indices, and hence this is a tensor of rank 2. Suppose if an index appears in the superscript as well as in the subscript, it has to be ignored while finding the rank of the tensor. For example, C superscript ik subscript jkl is a mixed tensor of rank 3. The index k appears both in the superscript as well as subscript, hence it is ignored. Hence we have I, j and l as the indices, hence this is a tensor of rank 3.